Welcome everyone again for this second talk by Aaron Naber of the Crossing series. Today Aaron is going to talk about Ricci curvature, fundamental groups, and the Milnor conjecture.
Okay. Well, thank you very much again for the invitation and for having me here. Again, I'd express my disappointment for not being able to be there in person. I'm gonna kind of continue with my co-workers of Milan series here and talk about joint work with Ilya Brue and Daniela Simola. So I've given this talk a few times, and each time it kind of changes a little bit. Each iteration, I try to add more pictures and remove big words, and hope it kind of converges to something understandable. So on the downside, I don't get anywhere near through all the lecture. So basically, at the end of the time, I'll kind of just quit. My goal is to make it a certain length, and then anything after that is just going to be kind of bonus. So the talk today is going to be on discussions surrounding the following conjecture by Milnor. So he conjectured back in '68 let M be a complete manifold, let it have non-negative Ricci curvature. Then the fundamental group should be finitely generated. And today's talk is going to center around a counterexample to this conjecture. That's joint work with Ilya Brue and Daniela Simola. So I think maybe the first thing to do is to sort of point out that the conjecture is actually remarkably close to being true. So in particular, what is true, what's known to be true at this point, is that if you take the fundamental group, and if you take any finitely generated subgroup of it, right? So just anything that happens to be finitely generated, then it is actually uniformly finitely generated. So that's to say something like if there's a subgroup that's generated by 1 billion guys, it's actually only generated by 10 guys. So this is a result which I'll talk about a little bit more later. It goes back to Kapovich and Wilking, building on the work of Fukai and Yamaguchi. And you know, among other things, what it kind of tells us is that everything you'd want to be a counterexample can't be a counterexample. You can't have too many z factors. You can't have too many z sub k factors. If you're going to have a counterexample to this, there's got to be something a little bit on the funky side about the type of group that can actually appear from all of this. And I'll discuss all this again a little bit later. But it's good to maybe compare this to say to higher homotopy groups. So if I'm talking about the second homology or the second homotopy group, as opposed to loops in the thing, then you can build examples, even compact ones, much less non-compact, but even compact ones, where pi 2 of the thing is infinitely generated. Actually, it's a z infinity out of this. It's just a whole bunch of generators kind of all tied up. The first examples like this came were due to Perlman and Mengai, and in fact, these examples are something called non-collapsed, and you don't need to know what that is, but what it basically means is they're really nice. Like from the geometrical world, it means they have kind of as many nice properties as you could have while still kind of falling in this class of non-negative Ricci curvature. And in the collapse context, one can do actually much worse. I mean, it turns out that you can even build examples here where at least in the limit, every open set in your space has infinitely generated second homology. So in particular, the thing can't be a manifold. I mean, it's all kinds of craziness in the limits, and these are fairly recent results with Eric Hupp and Kai Wong, my students. So I think the basic strategy here is we're going to cover some background and try to understand some of the theory that the conjecture inspired, and so understand what we can say about the fundamental group, and then we'll kind of try to do our best to draw some pictures and get a feel for what the counterexample looks like and what the real main points are as we go along. So kind of starting over now, terminology, just to make sure we're all kind of on the same page. MGP is going to be usually a pointed Riemannian manifold. So I'm going to take go. So I'm going to get my thing just messed up. Give me 1 second. guess that'll do. So M here is a Riemannian manifold. G is the metric on this thing, and P is just some point, typically speaking. That's some fixed base point living in the background. Sorry, my thing is messed up on me because, of course, it has. Won't let me slide my lectures anymore. Okay, so we'll wunderbar. Okay, there we go. Okay, so M tilde here will typically represent the universal cover of our manifold. And of course, it itself is just a Riemannian manifold, but the real point to keep in mind here is that when we have a tilde, we're usually thinking of it as a space with an action, right? So we've gone to a universal cover, and our fundamental group is acting as a group of isometry. So usually tilde means think about actions that are actually on our space floating around here. My general spiel about what curvature and Ricci curvature are kind of comes from the following. So if you are on Euclidean space, right, and if you take three vector fields, x, y, and z, then I could take the x and y derivative of z or the y and x derivative of z, and it doesn't really matter what order I take them in, right? I mean, it's symmetric. And if I'm on a Riemannian manifold, that becomes false, right? It's not symmetric. But at some point, somebody had the marvelous observation that if you look at the difference, this anti-symmetric part, which may not be zero anymore, although it looks like it depends on derivatives of z floating around here, it actually doesn't. So this curvature here, which is a so-called 4 tensor, it gives you three vector fields and gives you a vector field. It only depends on the value of x, y, and z at that point. So it's a tensor. And so this is the strict definition of curvature, but of course, this gives you absolutely no intuition for what curvature is supposed to mean. You should be interpreting curvature as being like the Hessian, the second derivative of the Riemannian metric, right? So if you sort of count indices for a second, that makes sense. So a metric has two indices, right, Gij, and a curvature is a 4 tensor, right? So it's got two more. So it's like you're adding one for each derivative. It's a 4 tensor. And it really does behave that way. So that is to say that, if I have a Riemannian metric and it has bounded curvature, then at least up to picking good coordinates, that means that your metric should be behaving kind of like a function with C2 bounds. And that this is roughly speaking kind of true. And it's the right way to interpret it. So that way, whenever people assume bounds on curvature, they're really controlling everything about the space to a certain degree, right? It's like having C2 bounds on something. It's a very strong condition. But this also motivates now what the definition of the Ricci curvature is. The Ricci curvature here is just the trace of the curvature operator, right? So I take this 4 tensor up here, I pair it with an orthonormal basis, and I start summing, and I get some 2 tensor out of it. But if you're interpreting the curvature operator here as the Hessian of the metric, then when I trace that, what I should be getting is the Laplacian. So you should really be viewing Ricci curvature as the Laplacian of the metric. And, if you're looking for a 20-word answer as to why Ricci curvature appears everywhere in places, it's basically for the same reason that the Laplacian appears everywhere in analysis. So, it's just Laplacians appear, right? And this is the Laplacian of the metric. So I think as a kind of an opening background here, what I'm going to do is give kind of a 20-line version of what my introduction to geometric class is. So my sort of intro graduate class in geometric analysis will do this slide in like complete detail, right, where you kind of define everything, improve everything, and go through the functional analysis. And we'll do it like one slide, but it'll give us it's basic enough that you can kind of follow, but it gives a hint without being too serious as to why Ricci curvature and fundamental groups should even be tied together in the first place, which is maybe not so clear offhand. So the starting point here is you consider the exterior derivative, right? So if you have a manifold, you have your space of forms on your manifold, and you have your exterior derivative, which takes a k form to a k plus 1 form, right? And sort of as a recollection here, right? This is like the anti-symmetric part of the derivative, right? So the derivative of something on a manifold requires geometry, but it turns out the anti-symmetric part doesn't. It actually is independent of geometry, and that's what the exterior derivative is. And it has this wonderful property that it squares to 0. And as soon as you have something that squares to 0 on something, it sort of screams to find a cohomology, right? And that's exactly what you do. So the de Rham cohomology classes, right, is you look at the space of forms and you look at those that are closed, right? So D of it is 0, and this is some big space. And you also look at those that are exact. So that is those that are D of something, right? And since the square is 0, this set here is inside of this set here. The set of things that are exact are inside the set that's closed. And you look at the quotient space. And amazingly enough, on a compact manifold anyway, let's say, this is a finite dimensional vector space now. And it's really topology, right? It's saying something about the topology of the underlying. It's basically the same as the R singular cohomology of the underlying space. So this there's this sort of connection between almost like derivatives now and topology through this exterior derivative, at least part of the derivative, the antisymmetric part. So what we'll focus on here is the dimension of these classes. So these de Rham classes. So the dimension is this topological invariant for each k. And when we look at 1, so we have the so-called beta numbers, Betti numbers of our space, which are the dimensions of our de Rham cohomology. And in the case of the first guy, it's related to the fundamental group. Okay, I mean, it's related to the fundamental group in this very kind of weak way, but nonetheless, you can recover it from the fundamental group, right? So if I use all the words, it's the rank. So this is a number, right? It's an integer. And it is the rank of the torsion-free part of the abelianization of the fundamental group. So it's just some small little part of the fundamental group, but it's definitely a part of the fundamental group that you get out of this. And now, being analysts, our complaint about this exterior derivative is that it's not an elliptic operator. We like elliptic operators. Elliptic operators are things that you can solve for and actually look at sets of solutions for, and they're well behaved. So what you do at this stage is you bring geometry into it. So there's been no geometry up to this point. And the geometry comes by looking at the adjoint operator. For this, you need a metric, right? And this is basically the divergence operator. And it takes a form to a k-1 form. And you sum the two things up, d plus d star. And what you get out of this is an elliptic first-order operator, or the way people tend to like to view it is you'll square the thing and make it an elliptic second-order operator. That's basically a Laplacian. So this is basically like a Laplacian on forms, and that's on this guy. And turns out to agree with the Laplacian up to some lower-order curvature terms. And in particular, it is a wonderful exercise, if you're kind of starting off in all this thing, to compute that this operator, say on 1 forms on your guys, like vector fields or 1 forms, is the Laplacian plus the Ricci curvature, right? And so hence we've got our first sort of introduction of Ricci curvature into this whole business. And a corollary of this computation is that we can say something topological. So if we have compact manifold, if we have non-negative Ricci curvature, then this first Betti number, which remember represents part of the fundamental group, it's the rank of the abelianization of the fundamental group, is at most the dimension of the manifold. Right? And then that actually follows from this. And very roughly speaking, how it follows is the following. Hodge had this sort of amazing equality floating around here that told us that, well, on the one hand, we've got this topological guy here, this Betti number. And on the other hand, if we go back up to this second order equation here, the set of solutions of this second order operator definitely depends on your geometry, because the equation itself depends on geometry. So what solves this Laplace-like operator depends on geometry. But the number of solutions does not. The number of solutions is actually completely independent of geometry, and the dimension of that space of solutions is exactly the Betti number of the thing. This is true for all k. In fact, I'm just stating it for the first Betti number. And so now we've got this connection between analysis, solutions of equations, and topology, this first Betti number. And so to try to control our Betti number, we can try to control the number of solutions of our Hodge-Laplacian. And so what we're going to do is look at a solution of the Hodge-Laplacian and then just ask, what can we say about it? And the first game you always play in this business is just integration by parts. So you take your solution, you're going to interproc both sides by your omega, you're going to integrate, right? Fine. You have, if this is 0, then this is 0 for silly reasons out of it. And then what you're going to do is plug in what we know, our sort of fun computation up here about what the Hodge-Laplacian is, into our d plus d star squared, our Hodge-Laplacian. And if we integrate by parts our Laplacian from this, then what we get is that this guy here becomes exactly the integral of the gradient of omega squared. plus the Ricci of omega. And this is now the sum of two non-negative guys if the Ricci curvature is non-negative, which means that if you solve this equation, then in fact, in particular, this guy here has to be 0. And it's got to be 0 point-wise because it's a non-negative guy. So what happens is that the covariant derivative of a solution's got to vanish. It has to be parallel. And what this tells you is that its value at any point is completely determined by its value at any other point, because you can just parallel translate it along any path you want and get its value somewhere else. So in particular, how many possible solutions can you have? Well, just pick a point. How many possible values can it take at that point? Well, it's at most the dimension of the space, which in this case is the cotangent bundle, which in this case is the dimension of the manifold, so n. So there is at most n solutions to our space, because we're completely determined by its value at one point. So that's it. I mean, that gives you at least a first little hint as to sort of why Ricci curvature and fundamental group are connected, at least even if it's in this kind of small little way. Estimates on the full fundamental group, which do come from Ricci curvature, are much harder. You can't really play integration by parts tricks to do it. You need a full structure theory in order to kind of understand all of this. But nonetheless, one can at least, hope and imagine at this point that something like this becomes true. By the way, you guys can stop me if there's questions at some point.
Actually, I have something very, very stupid.
Yeah.
The dimension of the solution is at most n. Isn't it exactly n? Can't you take any constant, basically? Or there is the Ricci thing?
But you don't know it is a solution, right? So you don't know that you can take this value here and parallel translate it here and actually get something independent of how you parallel translate, right? It's actually very hard to do. Mm-hmm. Right? So at most one for each direction, but you don't know they each actually determine a solution.
Okay. Thanks.
So case in point, right? If the Ricci curvature is strictly positive, so this guy here now becomes a positive, then there can't be any. The Betti number is actually 0, right?
Yeah, that actually makes sense.
Yep.
Any other question for now? Apparently not. Go ahead.
Okay. So now what I'm going to do, I'm going to talk a little bit about the background of the Milnor conjecture, just so we can sort of kind of have a setting for it all. So let me also maybe just open by saying this is not going to be completely fair. I mean, there's an awful lot of work that's been done on this. I'm going to try to point out what are really the major progress throughout the years and on all this. But I'm not always being as fair as I would like to be, given time. So this opens up with, not surprisingly, Milnor. So in 1968, he proved the following. Take a space with non-negative Ricci curvature, and take a finitely generated subgroup of the fundamental group. Then it's got to have polynomial growth. So this polynomial growth, this is a purely topological thing. It's something about the group itself, right? The group having polynomial growth is a group property. So he proved this sort of restriction on what kinds of groups can appear as fundamental group for the manifold. Actually, I also might add, he proved that the growth rate's at most the dimension of the manifold. Hence, maybe your first hint as to why you might think something like this is true. Because maybe if you get too many generators, that growth rate's got to actually go up, and that's going to stop at some point, right? So that this was, I'm guessing here, likely some original motivation for the conjecture. Some points to sort of mention about this that are fun. First off, he didn't call it Ricci curvature. And this is actually so old that at this point, there was different works. Some called it Ricci and some called it mean curvature. And as you maybe can imagine, due to things like minimal surfaces, that the mean curvature was kind of overused at that point. And I think that sort of died off at some point, and it just became Ricci curvature. And the other thing, which I think you'll probably, if you're a geometric analyst, you'll appreciate this, and otherwise maybe it's less amusing. But the proof is based on something called the Bishop volume comparison. If you're in sort of the business, one word you hear a lot is Bishop-Gromov volume comparison. Like this name appears constantly. This is pre-Gromov in all of this. And this is of course what led him to his conjecture. So I think maybe the first like work that's sort of worth mentioning kind of toward all of this was by Gromov afterwards. So Gromov proved the following, which is an abstract theorem that doesn't have anything to do with Ricci curvature. He proved that polynomial growth groups, so this thing that Milnor had sort of proved has to be satisfied by fundamental groups of non-negative Ricci curvature, are almost nilpotents. So their structure as a group can't be that bad. Like basically you've got a nilpotent group, and whatever's not nilpotent is basically finite, some finite extension of a nilpotent group. Although maybe I'll add, because it's actually important down the road, that there's no bounds anywhere here on how almost it is and things like this. I mean, there kind of can't be, the way he says this. So in particular, as a consequence, right, if you combine Gromov-Milnor, what you get is that manifolds with non-negative Ricci curvature finitely generated subgroups are almost nilpotent out of this. So they have a very reduced structure group in terms of what can actually happen to them. Gromov's proof is actually where he introduced the notion of Gromov-Hausdorff convergence. And actually, once again, if you know what this term means, that Gromov-Hausdorff convergence, this is a very metric notion. And if you aren't really in tune with the technical details of all this, it should be a little mind-blowing that this notion was introduced to prove this. Like they just don't look like they have anything to do with one another offhand. It's quite fascinating. And now I'm just sort of making my statement from before. So when you combine these two, you now have a reduction on the types of fundamental groups that can appear for spaces with non-negative Ricci curvature. So they can't be freely generated, for instance. They got to be almost nilpotent. They don't have to be abelian, but they're kind of close. Okay, so something to point out, this was actually a little bit later, but this is a good time to actually mention it, is that Wilking, and in particular Way, who sort of had the main jump for this, proved kind of a converse. So they proved that, on the other hand, all finitely generated almost nilpotent groups do arise as fundamental group of some space with non-negative Ricci curvature. All right, so up here you sort of said that they had to be, at least any finitely generated one, had to be almost nilpotent. And conversely, any almost nilpotent guy will be fundamental group of something down here. And this really began with Way, who provided the first example of a nilpotent lattice as the fundamental group. And this is actually very subtle and sort of deserves. First off, let me add, I think this might have been her thesis. I'm not sure about this. But it was 4 pages, which I love. Like, there's no fluff in this whatsoever. And it's worth emphasizing, because this is actually quite subtle. Because there is a conjecture by Fukai and Yamaguchi that if the sectional curvature is non-negative, then the fundamental group should be almost abelian. Right? And this is still open. So what she really proved with this is that this sectional curvature, non-negativity, can't be replaced with Ricci non-negative out of all this. So almost abelian becomes at least almost nilpotent in the Ricci case. And Wilking extended this by sort of building on these ideas to take it from some lattice to basically anything, and that's almost nilpotent. Okay, so sort of continuing, I would say the first really major progress for the Milnor conjecture was in 1978, and this was by Gromov. And what he proved was actually that he proved the conjecture if you have non-negative sectional curvature. So he showed that if you have non-negative sectional curvature, then in particular the fundamental group has at most some dimensional number of generators, right? A uniform bound on the generator, so clearly finitely generated. Just to throw the word out there, but it won't appear again later in the talk, he introduced the notion of short generators when he did this, which is a kind of something that also kind of appears quite often now. And the proof relies on the Toponogoff triangle comparison. And all that really means is to say that this is fundamentally sectional curvature, the proof. The Toponogoff basically, in 20 words or less, it lets you take behavior at infinity and pull it into behavior that's local. And so as soon as you're able to make that statement, it's maybe believable you should be finitely generated, because there can't be too much happening at infinity if you can relate to stuff that's happening more locally. The next major progress was by Fukai and Yamaguchi. So what they proved was a bunch of big words here, but essentially it's a local version of this. So if a space has a lower sectional bound, then the local fundamental group, which we don't really need a definition, but the definition basically means take the fundamental group of the image of the fundamental group of the ball into a bigger ball. It basically means take loops inside some ball of finite radius, but maybe let them contract inside of a bigger ball so that you don't get some nonsense that's occurring along the way. And they proved the same thing up here. They proved that you have to be uniformly finitely generated and almost nilpotent. So it looks like a local version of Gromov, but the reason it really deserves attention is that their idea is fundamentally different and fundamentally useful. It'll appear in the Ricci case in just a few minutes. So this is really where the ideas for controlling Ricci curvature really came from, is in their paper. Actually, what they did is they proved uniformly almost solvable, if I'm being very technical about everything. And just to be fair, it was extended by Kapovich, Petrun, and Tushman, the uniform case, which is actually quite tricky. Their proof really was much more than just Toponogoff. It requires a hefty structure theory, but luckily a lot of the structure theory actually can be repeated in a weaker fashion in the Ricci curvature context, at least at certain points. And the certain point business is what allows Fukai and Kapovich and Wilking to basically extend the results of Fukai and Yamaguchi to the Ricci case. So this is really like the big theorem in terms of controlling fundamental group of spaces with lower Ricci bounds. So ignore all of the locals here, right? So a corollary of this is that if you have non-negative Ricci curvature, then the fundamental group is uniformly finitely generated and uniformly almost nilpotents, right? So this was the first real structure theory for fundamental groups of lower Ricci curvature. So this is really a thing that I was talking about at the beginning. So once you have 1 billion generators, you actually have like 10 generators, right? So well, as soon as it becomes finitely generated, you actually can't have very many generators at all. You have a bound on the number that can actually appear. So in particular, things like too many Z factors can't be fundamental group. Too many Z sub K factors can't be fundamental group. Nothing that you would sort of like kind of want to write down as sort of being fundamental group of these things can actually appear as fundamental group of these things. If there's going to be a counterexample, something really funky has to be happening. And this was just sort of the point I mentioned. Okay, and let me just sort of maybe make one more remark as we're going along the examples. So in low dimensions, it's actually been resolved, the Milnor conjecture. So basically, in all these cases, it's because you actually prove much stronger topological results about the space. And the Milnor conjecture is kind of an obvious consequence, right? So it's done somewhat indirectly that way. So going all the way back to 35, it was actually known for surfaces that this is true. So in particular, if you have a surface, two-dimensional manifold, and it's got non-negative Ricci curvature, then either it's flat or diffeomorphic to R2. Right? So as a consequence, you certainly have finitely generated fundamental group. Like there's not that much to actually occur. This was extended in 82 by Shane and Yao. So what they proved is that if you have a 3 manifold and it has strictly positive Ricci curvature, then you're diffeomorphic to R3, right? So again, the Milnor conjecture is an obvious consequence of this because they've got a really very strong topological constraint on what can occur. It's really worth pointing out that the proof here is unique to everything else that I'm talking about in my talk. Because it really relies on minimal surface techniques inside here. There are quite a few papers out there right now where you'll assume positive Ricci curvature and then prove a bunch of stuff about minimal surfaces because it relates to the index formulas that are there. But this is really kind of unique in the fact that they go the other way, right? So that they prove Ricci curvature. I mean, if you assume positive Ricci curvature, you can say some stuff about minimal surfaces, but then they'll go back to use that to say something about the space itself, right? So that this is a very nice proof. And it was extended by Gonglu back in 2013. And he extended to the non-negative case, actually dropping that lower bound was not so trivial, and because you get more behaviors in this case. So essentially in this case, you're either diffeomorphic to R3 like in the positive case, or you actually split like R across a surface. So again, it kind of reduces down to the surface case, and you once again can say that the Milnor conjecture is satisfied because you really have this topological understanding. I don't want to talk about it because I feel like I'll be here the rest of the time, but let me point out that the Milnor conjecture has also been resolved under a large number of sort of geometric constraints. So basically, if you assume basically anything at all about the space and how it behaves at infinity, you can prove the Milnor conjecture is true. Right. So once you stop completely general behavior, So Lee and Sormani and Wei and Pan, they all have some very nice results on this that say that the Miller conjecture is true as soon as you make some geometric assumptions at infinity that are all kind of within the realm of reason. Okay, so there. So basically the combination of these results, so Gromov and Fukai and Yamaguchi, Kapovich-Wilking, they give us a really good structure theory for the fundamental group on spaces with non-negative Ricci curvature. They basically tell us that these things really can't be too wild. The main result of the talk today is to talk about a counterexample to this Milnor conjecture, and the precise statement is the following. So let's look at Q mod Z. So this is like the rationals in the circle, right? So just take the circle, look at all the rational points inside of it, right? Infinitely generated group. Take any subgroup at all you want of it, right? Some gamma. Then there exists a smooth, complete 7 manifold, right, with non-negative Ricci curvature, and whose fundamental group is that gamma, is this subgroup of Q mod Z. So maybe a couple of points. So first, for the rest of the talk, we'll primarily think of 2 examples. So we'll be interested in the case of Q mod Z itself, just the rationals on the circle. That's kind of the geometrically most fun example. But also we'll be interested in the dyadic group. So this is all rationals whose denominator is some power of 2. Mainly the reason to consider this case is that it will simplify a lot of notation later, and it'll make it a little bit easier to follow maybe some of what's being said. Important point. So there we go. Let's observe the following. Take a finitely generated subgroup of Q mod Z. Then in fact, it's going to be generated by a single element. So we've got these rationals inside the circle. It's an infinitely generated group. But if I have any finite subgroup inside of this thing, for instance, or any finitely generated subgroup, they're the same thing here, then by basically just taking the smallest element in it, that'll actually generate everything. So all subgroups of this thing are either infinitely generated or generated by a single guy, right? And that's in some sense exactly what's needed in order to slide around this result here. It's saying that you're infinitely generated, but all finitely generated subgroups. So anything you get by kind of looking locally is actually going to be generated by one thing in this particular example. And let me sort of mention the following. So if you've never really thought about it before, just building a smooth manifold that has the rationals and as its fundamental group sounds funky. There are no methods for doing this. Probably the most geometrically popular of them is the sort of dyadic solenoid complement. However, it's sort of worth pointing out that even from a topological perspective, the way we build these guys is actually quite distinct from anything that's in the literature. I gave a rather painful talk to a bunch of topologists just to sort of kind of confirm this point because I wasn't so sure when we first did this. Oh yeah, and let me go ahead and mention that more recently we've also built a 6-dimensional counterexample. So 4 and 5 are still open. I think they're both harder. I don't think you're going to use these ideas to build a 4 or 5-dimensional example. Certainly not a 4-dimensional one, and that's going to be much more challenging. I will, however, focus almost entirely on the 7-dimensional example in our construction. The reason being is that I think it's a little bit more pictorially clear. It's a little bit easier to wrap your head around what's going on in the 7-dimensional example and the 6th one. They're kind of similar, but the certain aspects of them are a bit different. Okay, and then maybe let's mention some geometric properties of these guys. So the 7-dimensional counterexample. So the first point is that these were actually all proved along with the 6-dimensional example. So we kind of figured out most of this after the fact. So the universal cover of this space, but with the funky fundamental group, is actually really simple. It's just diffeomorphic to S3 cross R4. In fact, we didn't know that originally. In fact, our original thought was that pi 3 of it was infinitely generated, because the way this is going to be built is we're going to keep sticking in new S3s as we kind of keep going along. The fact that these sort of, magically at infinity all unwind is highly unclear, actually, and this was not our first thought. And geometrically, for every kind of small number eta, we can build the example so the followings hold. It's actually going to have bounded sectional curvature, in fact, small sectional curvature, right? And in fact, at infinity, okay. At infinity, the sectional curvature is going to actually decay quite quickly. So geometrically, it's actually becoming quite flat at infinity. One should be a little bit careful about how fast it's becoming. It's not really becoming. It's not scale invariantly becoming flat. It just sort of looks flat without the scale invariance. If you're a geometer, you'd be sort of interested in knowing that it's locally non-collapsed. So the volume around each ball is bounded from below, like half the Euclidean ball or something. But at infinity, the volume's nuts. So if I look at the volume of large balls in this space, basically it can be whatever I want. So it can grow at like a Euclidean rate, so r to the 7. It can grow at a very small rate, like r to the 4th. They actually grow at basically any rate in between the two. So the volume is sort of moving, anything you want at infinity. It's sort of cycling around stuff. And as sort of behaviors at infinity of what this thing looks like, its behavior at infinity is constantly changing. Like it doesn't have a behavior at infinity. It has, from the technical standpoint, it has non-unique asymptotic cones, and this non-uniqueness is well, actually, there's an infinite number of possibilities as you're kind of going along. So geometrically at infinity, it'll sometimes look like a cone over a lens space. So this is, imagine, you've got like an ice cream cone, but inside that cone there, you've got like S3 mod some quotient. But every possible lens space appears inside this. What'll kind of happen is that it'll look at infinity, and then it'll sort of open up and look at like this sort of ice cream cone with a lens space, kind of a Pac-Man thing, and it'll close down to a half ray, which I think is what I say next. And then when it reopens, you're going to have a new lens space, but it's a different lens space. So it'll have kind of a mouth that's now a different quotient of a sphere. So it'll kind of just keep doing a Pac-Man thing in infinity, where it closes to a half ray, reopens as a lens space, and then every time it reopens, it's a new lens space. So there's some crazy behavior at infinity. If you geometrically inclined, you want to compare this to all the previous results about, when Milnor conjecture is true, trying to follow through how it sort of slides around them all and actually remains true is actually sort of a fun game. Okay. So my last 10 or 15 minutes, what I'm going to do is I'm going to go through the steps of the construction a little bit and try to draw some pictures for us in terms of what might be happening. Good time for questions because it'll get worse now. Okay. So let's talk about the steps of the construction real quick. So what I'm going to do is I'm going to use a bunch of words and I'm going to draw some pictures. Typically, I like to draw the pictures on a blackboard next to this, right? Since we're doing this online, the pictures will kind of appear and disappear because I'll try to throw them in there so we can look at them, but then I necessarily have to move on to the next thing. It's nice to have them stay, but it is what it is. So the construction, let me first point out, doesn't focus on M. So I don't try to build a space here. We're not trying to build a space with a funky fundamental group. What we're actually trying to do is build the universal cover. So we want a simply connected space with a funky group action on it. That's actually what we're looking for in the end. So we're looking for, and I'm going to focus on the dyadic group here. So that is, rationals who inside the circle whose denominator is some power of 2. This is an infinitely generated group. And essentially the reason for choosing this is that it will simplify some notation as we move along, right? In some sense, the general construction looks the same, but I'll try to point out where maybe some differences are as we move along, but hopefully I can try to throw away as much complication as possible. The construction will be inductive in nature. So for each j, what I'm going to do is I'm going to build an example, some mj tilde. It'll be a complete manifold with non-negative Ricci curvature. It's going to have a free and proper action by a finite group gamma sub j. This finite group is going to be generated by just 2 to the minus j. So it's sort of this is as a group. It's sort of like z sub 2 to the j, I guess, right? So when I go from g to j plus 1, what I'm basically trying to do here, right, is we're trying to add one extra generator to this thing, right? So the number of elements of our fundamental group will double each time we kind of go up. And that doubling will basically add a new generator, and that new generator will generate the old generator as we're kind of going through. So pictorially, a nice way to sort of see this is like this, right? So gamma naught is just like the identity. So here's my gamma naught is just like 1 point. Gamma 1 here is generated by a half, right? So this is like just z sub 2. And that means that it's this guy and this guy. And here's my generator for gamma 1. Gamma 2 now is generated by a fourth, so it's like z sub 4 is generated by this guy up here, right? Note that when I take my gamma 1, the generator of big gamma 1, I square it, I get the identity. Note that when I take my gamma 2 and I square it, I get the generator of gamma 1. When I go to gamma 3, which is now generated by an eighth, right? Then when I square it, I get the generator of gamma 2, which when I square, I get the generator of gamma 1. In other words, every time we go up, the new generator that we're adding to all this squares to the old generator, right? So that's this basic property of always being generated by one guy, right? But in the limit, it'll be infinitely generated. So we're adding one generator each time, essentially. And the construction itself is going to involve three main steps, right? And I'm going to try to basically focus on one or two of them. So the first main step here is going to be to build a background model. So essentially, we're going to build this guy by gluing together an infinite number of copies of S3 cross R4. Hence the fact that you are in the ind S3 cross R4 is not so clear. So we're going to glue an infinite number of these guys together. And at each time when we kind of start over to build our next space, we're going to have kind of a background model space. And what it's going to look like is, let's just throw the whole thing out there. So our S3 cross R4 here, right? So my R4, I've given it a little bit of an angle just to show some positive curvature if you want, but think of it as being very close to R4. It'll be S3 cross R4. It'll have some action by this gamma sub j that'll be quite wild. So on this S3 cross R4, it'll be rotating the S3 at some slow, perfectly normal way. But on the R4, which is like a cone over S3, right? So you can rotate that S3 factor inside there too. It's going to rotate very, very fast. So as j gets big, we're going to kind of always start over with an S3 cross R4. But each time we start over, it's with a worse action. The action is going to be rotating things faster and faster and faster as j gets big. And the idea for building mj from mj minus 1 here is that we're going to take this background space here, which has this larger group action by gamma sub j, and we're going to plug in 2 copies of our mj minus 1 into it. So we're going to plug it in so that our new generator, because remember, we just basically add one generator each time, we'll map this guy to this guy, and then when you have to get in, it'll kind of come back, but it won't come back trivially. It'll come back in a way that twists it to become the right action here, right? So this is an equivariant gluing of all the actions. So in this way, we kind of want to repeat this process over and over and over again until we have this sort of global object that we can build from. Okay, so maybe I'll point out if this wasn't the dyadic group but Q mod Z, I may not glue in 2 guys. You might glue in like some K number of guys. So each time you'll glue in a finite number of guys, but it may not always be the same finite number of guys. Okay, so the really hard part in all of this now is that, what I sort of emphasized a second ago is that we have this mj minus 1 here, our last step. We've got some crazy looking action on it. We've also got some crazy looking action on this S3 cross R4. But when we glue them together, the actions need to be compatible. And it's maybe not going to be completely shocking to say that they just aren't. I can't take 2 crazy actions and glue them together in a compatible way. It's not possible. So what is by far the hardest part of all of this, so step 2, is that I have to untwist my action at infinity. So what is going to occur, here's a picture. Well, here, I'll say the words and then I'll show the picture then maybe. So this action is going to be highly, highly twisting at infinity. And what I need to do is do something funky to all of it, to unwrap it, and make it look really simple at infinity. So with this crazy action, I can't glue it into my base model. So what I need to do is basically untwist it. And the picture's a little bit like this. So what happens here is that I've got my S3 cross R4. That was like my base model from before. I have down here, like view the bottom here is like the original base model that we're kind of working with and gluing from. Or if you want, it's the infinity of the MJ minus 1 that's being glued into it. With a really crazy action that rotates both this S3 and it's rotating this R4. So the S3 that's kind of, it's a cone over, right? You've got the 3 sphere inside of the R4. It's rotating that. But it's rotating it really, really, really fast inside here. And what's going to happen geometrically is that it's going to kind of fold up. It'll look kind of like a cone over S3 cross S3. So fun game. Remove a small ball from R4, then that's the same thing topologically as removing a small ball from the cone over S3 cross S3. So instead of viewing this as S3 cross R4, when you move up, you can kind of view it as being a cone over S3 cross S3. Geometrically up here, you're going to do something crazy. You're going to be unwrapping a whole bunch of stuff. And when you come back out of it again, you're going to look geometrically exactly the same. You're going to look down here, you're an S3 cross R4, no problem. Up here, you're an S3 cross R4, no problem. Down here, you've got this crazy group action that's rotating everything. And you don't like it because you can't glue that into something in a reasonable way. But when you come back up the top, it's only rotating the first S3 factor. That's all that's occurring. So it's a very simple action. It's really easy to actually glue into something. Now, the problem here is that I've basically got these two actions, which are basically both on S3 cross S3, because you're basically rotating the S3 factor, and the S3 factor, your R4 is kind of the sphere of that thing, right? They're really both S3 cross S3 actions. Down here, you're rotating both factors. Up here, you're rotating only one factor of it, so it's simplified. These two actions are not homotopic. So I can't actually go, like I can't have a continuous family of actions floating around here that start down here and end up here. So the question becomes, how do you actually continuously change to start and stop between two things that you can't get from continuously between? And the answer is basically that this S3 cross S3 and this S3 cross S3 are not the same. Well, what's actually happened here is instead of changing the action, because I know I can't change the action from here to here, I've changed the S3s. So I've mixed them together in a way where this S3 is now mixed between both of them. This S3 down here is mixed between all of them. So when it comes out the top, it's actually the same action. But geometrically, if I write it to look like S3 cross S3 isometrically, it now looks like it's only acting on this 3 sphere here, even though it's actually the same as this action down here, right? And the other way to say this is that to get from this S3 here to this S3 cross S3 down here, you're going to act by these two S3 cross S3s are isometrically the same. So there's a diffeomorphism between them that preserves the isometry. But the isometry is not the identity map. In fact, it's not even homotopic to the identity map. It's mapping class non-trivial, as it turns out. So we're going to move between these two non-continuously things by changing the geometry continuously, so that in order to identify these two S3 cross S3s, that forces you to have a diffeomorphism that isn't the same at the top and the bottom. So you identify two things in a non-continuous way by changing the geometry continuously between them. Okay. So since I am running short on time, maybe what I would like to do is have a global picture of the whole thing. So that's slightly cleaner picture of the whole bit. Right? So we've got a sort of base model down here with our S3 cross R4, and we've got our double actions that we're sort of moving in. We untwist it, we make it look nice and clean, and then we glue it back into our S3 cross R4 down there, and we do it again. And you just do this process over and over and over again. And essentially, if you're trying to identify what actually happens to this guy topologically, you can think of in terms of ignore most of the words here. In terms of a graphing tree, right? So from a topological perspective, what has happened here is that we're looking at a tree. We have the edges, each vertex of the tree is a copy of S3 cross R4. So these are all the things we're gluing together. Each edge here represents one of these gluings that we just did kind of geometrically when we were gluing it back before. And we have an infinite number of copies of everything because we keep doing this over and over and over again. So we see that our space is sort of modeled on a fractal underneath it. The fact there's 2 going into each was the same reason that there were 2 in our picture going into each, and this was because it was the dyadic group. So if this was Q mod Z, you would actually have some finite number of arrows kind of moving from one vertex to another collection of vertices. Okay. So maybe what I'll do in my last 1 minute here is I can state something sort of independently that we can maybe understand independently of everything else. So even if the last minute was fast and I lost you can sort of recover for this point here. What is happening here, that this process of this weird twisting I was talking about going on with the geometries, the effect of that is that these gluing maps from S3 cross R4 into S3 cross R4 are mapping class non-trivial gluing maps. So I don't just care about building this space with this funky fundamental group. I care about doing this in a geometrically relevant way. I'm trying to preserve Ricci curvature in this process. And so what this is suggesting to us is that we need to figure out what the relationship is between mapping class groups, so diffeomorphisms, mod, homotopies, and Ricci curvature, right? And there's a very nice clean theorem that we can state for this that I'm going to go ahead and kind of state. So first, recall mapping class group, right? So I look at the diffeomorphisms of S3 cross S3, and I'm looking at the connected components of that, right? So this is, if I have two diffeomorphisms of S3 cross S3, and they differ by some sort of homotopy of diffeomorphisms, then we'll call them the same, right? And this is an actual group, and we call it the mapping class group. So our gluings here were elements of the mapping class group, non-trivial elements of the mapping class group in order to twist this action. And the theorem here is the following. In fact, what we proved is a bit harder, but this is a corollary and it's easier to kind of get your head around. So take the standard metric on S3 cross S3. We have 2 spheres, right? S3 cross S3. Let G1 be the pullback of the standard metric by your favorite diffeomorphism phi, whatever that happens to be. So G0 and G1 are basically both the standard S3 cross S3 geometries, right? But they look different in coordinates. Typically speaking, if you're a geometer, you consider them to be the same because it's just a coordinate expression, right? So these are both the standard S3 cross S3s, but they look quite different in our coordinates. Then the theorem is that for any diffeomorphism, there exists a smooth path of metrics, G sub t, on S3 cross S3, with positive, all of which have positive Ricci curvature, and it starts at the standard S3 cross S3, and it ends at this pullback S3 cross S3 that you get by pulling back by the diffeomorphism. As kind of a reality check here, if this diffeomorphism was homotopic to the identity, this would be completely trivial, right? Because you could let the G sub t's all just be pulled back to the standard metric through diffeomorphisms, and then you'll clearly start at one end and the other, and it doesn't matter. But in the case where the diffeomorphism is not homotopic to the identity, then actually being able to connect these 2 guys, these G sub t's are pretty wild looking geometrically. Like it's not so easy. The fact that you're kind of the space of positive Ricci is invariant under the sort of mapping class group action of it is not at all clear. But it is true, and this is the basic construction we need in order to say that we can do this weird twisting in a way that preserves geometry in the end. And I think that's probably about as good a time as any for me to quit, so thank you very much.
Thank you for your talk. Is there any question? Sorry, 1 second. Give me time to...
Thank you for the talk. So the 2 questions. First, can you give us a brief idea of what, or longer as you wish it, or what the 6-dimensional example is? Well, maybe it's too complicated, I don't know. And second, can you give us an idea of why this lemma is true? So what is important in S3 for this to happen? Is it because is the group structure important? The fact that itself is diffeomorphic to early group, or something else? I don't know.
So, okay, so for the first question, the six-dimensional example is basically just a whole bunch of copies of S3 cross R3 instead. So formally speaking, it looks very similar to this. The thing that makes it harder, and in fact really harder, is actually exactly this lemma, proving the version of this lemma in that context, because here we've got this S3 cross S3. So having the version of that lemma for that actually turns out to be much harder, as it turns out. There's certain simplifications we do here that you simply can't do in that context. But formally speaking, it looks very similar. But it's easier to connect the mapping class group to this particular example, which is why I focus on the 7 dimensions. In terms of how you prove this, so essentially, it's done, I mean, so really what's proved is something a little bit different and a little bit stronger. An equivariant version of this is proved. So what happens is that actually you want to prove, you only need to prove this for enough diffeomorphisms that generate the mapping class group, first off. You don't really have to prove for all diffeomorphisms. And in this particular case, what you really want are diffeomorphisms that'll conjugate these actions. So these weird actions that rotate both, or the action that rotates one, they are conjugate even though they are not homotopic. So you want those diffeomorphisms. And so in that case, what you can do is you take your S3 cross S3, and there's an infinite number of ways, basically, as viewing this as an S1 bundle over an S3 bundle over S2. And these ways are actually not at all clearly isomorphic to one another. But essentially, in the end, we build geometric isomorphisms between them to sort of see how you slide from these different ways of representing S3 cross S3 as an S1 over an S3 over an S2 bundle. And then we follow the geometry along with that. In fact, not all the construction is even explicit. Some of it's just sort of theoretically existence. Because we have to build, at certain points, we have to build Yang-Mills connections over the S1 bundle. And the way we actually build some of the homotopies are more of a theoretical, we know it exists, but exactly what the path looks like, we don't know kind of construction. So it's done semi-explicitly. We've had this sort of explicit way to represent it, but at steps, you have this very inexplicit, we know these things exist, but we don't know what they look like type of instructions.
Any other question? Okay, if this is not the case, then let's thank Aaron again.
Thank you, guys. Thank you very much.
This was okay.